Hi everyone, this video takes the liquefied gas cylinder as an example to introduce the acoustic emission testing procedures and the SAEU3H multi-channel acoustic emission instrument operation guides. The SAEU3H instrument is a new generation acoustic emission instrument using USB 3.0 technology. It has 300 megabytes per second of a single USB cable transmission speed. The newly designed aluminum alloy case brings better electromagnetic shielding and heat dissipation effect. It has a variety of machine status indicators, plug-type channel connectors, and channel LEDs. Each AE card has 4 AE channels so that it's more compact and portable. Each SWAE can be used independently or cascaded to form a system with a maximum of 256 channels. This operation uses a liquefied gas cylinder as an example. The diameter of the gas cylinder is 400 mm and the total height is 600 mm. Its material is Q345 low alloy steel. For complete acoustic emission testing work, it mainly includes the testing preparation, on-site testing, data processing and analysis, finished with reporting. This video focuses on equipment operations and field debugging inspections. First of all, a preliminary detection scheme should be formulated according to the detection objects before the on-site detection. The content mainly includes the sensor layout scheme and the loading curves of the equipment. For the gas cylinder, we made a local detection of the overall part. So we formulated a sensor layout scheme for 2 rows and 3 columns. We take one sensor installation as an example. First, mark the sensor position on the surface of the container and polish to reveal the metallic luster. The size of the revealed surface should be larger than the receiving surface of the sensor. The sensor is connected with a coaxial cable. Evenly coat the receiving surface of the sensor with the coupling. Couple the sensor to the installation position and fix it firmly with a magnetic holder. Gently wiggle the coaxial cable from the sensor output to make sure the receiving surface is well coupled to the container surface. Install all the sensors to the container according to the layout plan and connect them to the acoustic emission instrument. Connect the USB cable from the AE host to a computer. Open the acoustic emission software SWAE on the computer. The device on-site operations can be roughly divided into the following steps. First, acoustic emission signal acquisition settings. Second, software views and location settings. Third, equipment debugging. Click the Hardware Sample menu and then click Sample Settings. In the Hardware Setup page, what we need to set up is the filter. According to the standard requirements of the detection purposes, the filter is set as 100 kHz high pass and 400 kHz low pass, which means the detection frequency range is 100 to 400 kHz. In the Heat Features page, we need to set the threshold, heat definition time, heat lock time, and peak definition time. Set HDT as 2000, HLT 20,000, and PDT 1000 microseconds. Click Waveform button to set the sampling rate and sampling length of the waveform. The sampling rate can be up to 10 MHz. When the standard requirements are met, it is a more balanced choice with 10 times of the detection frequency range. Let's set it to 4000 kHz. Other settings and options such as the synchronization mode are kept as default for this test. Click the Saving button to enter the file storage settings. It shows the file path and the file name to be stored in. Be sure to check the Save Acquired Data option. Set the maximum file size and number as big as possible depending on the size of your computer memory. For other settings, keep it as default. After the hardware sample settings, set up proper views based on the test requirements. Click the View menu and then click Merge, and the software will clear the default views. Click Split and move your mouse to draw the table size. For example, 2 by 2 for a total of 4 views. After left-click to confirm, 4 blank views are created in the view area. Click on a blank area and choose the view types on the top. First, create 2 basic and commonly used data views, data table and waveform graph. In the third view, select the correlation graph. In the setting area of the correlation graph on the right, you can set the x-axis, y-axis, and the display mode of the correlation graph. For example, the default x-axis is the channel number, and the y-axis is the hit number, which represents the comparison of acoustic emission hits received by each channel. Additionally, multiple correlation graphs can be set, such as the amplitude and time diagram, which represents a trend of amplitude changes over time, and it is often used for background noise acquisition to better determine the detection threshold. Finally, build a location map. According to the LPG cylinder, select cylinder graph in the location wheel option. In the cylinder setting, enter the relevant parameters, such as diameter 400 mm, cylinder length 700 mm, which means the vertical spacing of the upper and lower rods of the sensors. The number of rows is 2, and there are 3 sensors in each row. This time, the bottom part of the tank is partially detected, so no end caps is selected. The event setting and location setting can be set later in the machine debugging stage. After setting up the signal acquisition and views, it's time to debug the device. Equipment debugging is divided into 5 parts, including the sensitivity test, attenuation test, background noise measurement, sound velocity measurement, and the positioning calibration. The first step is the sensitivity test. According to the test standard requirements, the sensor sensitivity is calibrated using the pencil lead brake signal as an analog source, 10 centimeters away from the sensor. Every time, the pencil extends the lead for about 2.5 mm. The guide ring is attached to the pencil tip. Move the pencil to the surface and break the lead. Each sensor requires the pencil breaks for 4 times. In the data table, you can see the parameters of the heat feature signals. Clicking on the amplitude column title can rearrange the amplitudes in the ascending or descending order. Pencil lead braking signal is a strong and standard acoustic emission signal and can be easily found based on the high signal amplitudes. Record the highest amplitudes for each pencil brake and average the 4 braking signal amplitudes as the sensitivity value of the sensor. Ensure the sensitivity values difference between the sensors are less than 4 dB. If the difference is bigger than 4 dB, couple the sensors again or replace them. The second step is the attenuation test, which aims to get the attenuation curve of the signal conduction in the container. Combined with the background noise, it is used to confirm the maximum feasible sensor spacing and evaluate the real length of positioning time. In order for the convenient observation, choose only one channel and close other channels temporarily. We use sensor 1 for the attenuation test. First, along the direction of the two sensors with the maximum spacing, such as the direction from sensor 1 to sensor 4. Select some test positions away from sensor 1 for 10 cm, 40 cm, 50 cm, 80 cm, etc. The maximum distance for the attenuation test should not be less than the maximum sensor spacing. The pencil lead will be breaking off at each test position for 3 times. The signal amplitudes and the corresponding distance of the pencil lead breaking were recorded. The attenuation curve can be plotted using the mean values of amplitudes at each breaking points and their corresponding distances. The third step is the measurement of background noise. Background noise determines the detection threshold. Decrease the threshold to a lower level, for example 30 dB or lower, and start to collect data. Observe the amplitudes of the collected signal in the data table, or establish a time and amplitude correlation graph for the amplitude chance in order to determine the noise level. According to the standards, the detection threshold should be 6 dB above the background noise level. For example, the background noise in the test was 32 dB, so the detection threshold should be 38 dB. In some cases, the noise level is not consistent from channel to channel. Therefore, the threshold for each channel may also be inconsistent, especially when detecting large containers. Step 4. After setting the detection threshold, you can measure the speed of sound. Sound velocity is a very important parameter in the location calculation. We choose 2 sensors with the maximum sensor spacing, that's sensor 1 and 4. On the extension direction along the connection of sensor 1 and 4, give a pencil lead break signal. Find and record the arrival time of the pencil lead breaking signal received by sensor 1 and 4 respectively in the data table. Because the distance between sensor 1 and 4 is known, divide the distance by the arrival time difference to get the speed of sound. For example, sensor 1 and 4 are 780 millimeters apart. We can get the arrival time difference, and therefore the speed of sound can be calculated by dividing 780 millimeters by the arrival time difference. Step 5. After the sound speed is measured, select the location view and click the Locate Settings button and choose Event Setting. In this interface, we need to set the parameters related to the positioning calculation. First is the amplitude deviation. The principle is to be bigger than the maximum difference of the sensor sensitivity. For components with low attenuation material and complex shapes, it should be even bigger relatively. Here, we set it to 6 dB. Second, define the event definition time, which should be greater than the maximum sensor spacing divided by the speed of sound. In the case of this cylinder, the maximum sensor spacing is 780 mm, and the measure of sound is 5 km per second. Multiply the division result of these two by a tolerance factor of 1.2 to obtain the event definition time. The event log time is the log time after obtaining a set of event locating parameters. No event locating calculations is performed during the time. The default value of this parameter is retained. The heat interval is the same as the event definition time in the triangular positioning events. In the polygon locating events, It should be greater than the length of the longest side of the polygon divided by the speed of sound. The triangulation is used in this detection, so it can be the same as the event definition time. Keep the other settings as default. Click the location setting and enter the sound speed calculated previously and confirmed. Next, conduct the precision and calibration test. The detection threshold, sound velocity, and other parameters have been set in the previous steps. Before the device loading test, a precision and calibration test should be conducted to check the precision accuracy. Start the data acquisition and do the pencil lead breaking tests in the triangle areas formed by sensors. Record the actual breaking precisions and observe the calculated hit precisions in the location view. Compare the actual and calculated precisions. Each precisioning event should correspond to each lead breaking signal respectively, and the precisioning error should not be greater than 5% of the maximum sensor spacing. After the precision and calibration test, the equipment debugging before the detection is completed, indicating that the equipment meets the conditions for acoustic emission acquisition work. In the loading test, the detection container will be loaded according to the preset loading curve, and the equipment will collect the acoustic emission signals during the whole loading period and save the original data. The testing personnel should monitor the software data in real time and determine the processes in the field if the data results are abnormal. After the detection, a secondary sensitivity calibration should be carried out for all the sensors to avoid significant changes in sensor sensitivity during the detection. If there are events loading significantly concentrated at the area on the location map, use the coordinates to determine the specific location of the sound source in the container. After the completion of acoustic emission detection, the information saved or recorded includes but not limited to the basic information of detection object, the loading program, the sensor layout, the original data record sheet of the equipment debugging process, and the original acoustic emission data during the whole loading period. At this point, the field testing is basically over, and the subsequent data should be processed and analyzed according to the testing standards, and the test report should be issued. If you want more information or have any questions, please don't hesitate to contact us. Thanks for watching.